Hello, this is the next video in a playlist I'm calling General Linear Models Design of Experiments. And this is a follow-up video where we looked at the projection matrix onto the column space of X. And actually that's a video that I strongly suggest you watch prior to this video. And this video is an example using the methods that we derived and examined in the previous video. Now the model that we're looking at is this. It's the effects model. So y equals mu, which is a grand mean, plus tau I, which are the shifts in the mean effect, plus, epsilon, which is some error fluctuating about the group means. I equals 1 to 2 and j equals 1 to 2. So there's two groups, two observations in each group. And we did that just so we could do these calculations by hand. EIJ are the mutually uncorrelated and mean zero and constant variance sigma squared. Now let's write this in matrix form, which is this. So y equals x beta plus epsilon, where the expected value of epsilon is the zero vector, and the variance of sigma squared is sigma squared times I. Now y, remember I is 1 to 2 and j is 1 to 2. So this is y 1 1, y 1 2. So these are the first two options in group 1. And then it's y 2 1 and y 2 2. So these are the two options in group 2. The beta vector is mu tau 1 tau 2. Of course the epsilon vector is epsilon 1 1, epsilon 1 2, etc. But the design matrix, this one is in group 1, which is tau 1, not tau 2. So when we do this multiplication up, we get mu and tau 1. And then the same way here, mu and tau 1. But this one jumps to group 2, so that's a 0 and this is a 1. So anyway, so this is the design matrix. Now let's find X transpose X. And a lot of these matrix multiplications, I have them written out so you can pause the video and go through it, but I'm not going to. So X transpose X is this, 4, 2, 2, etc. Now we want to show that G1 by this matrix is a generalized inverse of X transpose X, this. And then we want to find M, the perpendicular projection matrix onto the column space of X, using this formula that we derived in the previous video. Now to show that it is a generalized inverse, you take X transpose X times the generalized inverse, which we're proposing is this, times X transpose X, and that should equal X transpose X. So we plug in X transpose X, the generalized inverse, X transpose X, and we do the multiplication and we do get X transpose X back. So this is G1 is a generalized inverse for X transpose X. So now when we calculate M, we'll use this generalized inverse matrix right here. So in the next video, it's M, and then the formula. So this is X, this is the generalized inverse of X transpose X. This is X transpose, and we get this matrix. Now, notice in the upper left it's 1/2, and in the lower right it's 1/2. It's not diagonal, because if it were a diagonal, there would only be elements on the diagonal. But this is called block diagonal. So if you think of it as a block, and then the next block down, and down the diagonal is filled. So this is what's called a block diagonal matrix. And that is the perpendicular projection matrix onto the column space of X. Now, let's show that G2 is a generalized inverse for X transpose X. Generalized inverses are not unique. If there's one, there's usually a million, or infinite. So, and then we want to find the perpendicular projection matrix. To show that it's a inverse, we have to calculate this and it should equal X transpose X. So we fill it in. This is X transpose X. This is the generalized inverse that we're proposing, X transpose X. Do this calculation and we get this, which is X transpose X. So this G2 is a generalized inverse of X transpose X. So now when we calculate M, we have to do this. So X is this, so it's the design matrix. Generalized inverse, which we're going to plug in this next one. And the next transpose is this. Do the calculation and we get this. And it's the same block diagonal that we calculated before. So even though we used a different generalized inverse, the perpendicular projection matrix is the same. And the theory tells us that they have to be, because perpendicular projection matrices are unique. And there we have it. So now let's do another example. So let's only use columns 2 and 3 of the design matrix X to calculate M. And I'm going to flash it back here. So here's the original model. And we're only going to use these two columns. Now, notice that column 2 plus column 3 is column 1. So it's kind of redundant. So let's just use these two columns. So we can't call it X because it's not the design matrix. So let's call it X star, which is columns 2 and 3 of the design matrix. Transpose X star, which we plug it in and we calculate it and we get this. Now this is non-singular, so it has an inverse. We don't have to calculate the generalized inverse, and it's this, so it's 1/2 down the diagonals. Now let's calculate M. So, X star transpose, X star inverse, X star transpose, and then we just plug it in. So this is the first two columns and the inverse that we calculated, and that's X star transpose, which is this. We do this matrix multiplication and we get this. It's the same block diagonal that we calculated in the previous two. So this one, we use this generalized inverse. This this calculation used this generalized inverse, and this used a totally different method, but we have the same perpendicular projection matrix. So the notes are this, that in M, in 3 and 4 are equal because perpendicular projection matrices are unique for the same vector space. So in this case, the column space of X creates a vector space. But now, why is this perpendicular projection matrix in 5 the same as 3 and 4? And here's the reason. Because M in 5 is equal to M in 3 and 4 because the span of these two vectors, columns 2 and 3, is 100% the same as if we were to span these three vectors, because that first vector is redundant. It's really not needed, adds nothing to it. So the span of these two, the span of these two vectors is equal to the span of these three vectors. They create the same vector space. So the perpendicular projection matrix onto these two columns is 100% the same perpendicular projection matrix if we span these three columns, because this one is a dependent vector. So they're the same vector space. So they have to have the same perpendicular projection matrix because perpendicular projection matrices are unique. All right, so one more. So now, in the first video, I would say, we have a dangling y out there and we pre-multiply it by the perpendicular projection matrix. And dangling is just my, sort of silly, funny way of saying we have a y vector in space. It's there somewhere, and if we pre-multiply it by the perpendicular projection matrix, it actually projects it down into or onto the column space of X. So let's see if that's the case in this one. So let's pre-multiply y by M, which is M times y, and it projects y onto the column space of x. So let's look at that. So my, so this is m, remember it's the block diagonal matrix, and this is a generic y. And notice when we do this multiplication that we get y11 plus y12 divided by 2, which is really the mean of group 1. So it's y1 star bar. So this is the mean of group 1. And if we do it for the second row, we get the same. And for the third row, it's the mean, the group mean of 2, which is this, the same way for the fourth row. Okay. Now let's look at this in more detail. This can be broken up into this. So y1 dot bar, so the group mean, group 1 mean times this vector plus the group 2 mean times this vector plus 0 times this vector. Now notice that these are the 3 columns in the design matrix. So my is a linear combination of the column space of x. So it is and lives in the column space of x, just like we said it should. This is a linear combination of columns of x. So M does project any dangling y vector down onto the column space of x. Anyway, I just find this stuff so fascinating, and it just works and makes sense. And it's going to help with the theory as we proceed if you kind of get a hold or a feel, an intuitive feel or geometric feel of what's going on for design of experiments. Well, I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.